data structures, there are 1, 2, 3, 4, 5, 6, 7 different important parts of data structures, split into 3 subtopics. So arrays. Arrays are data structures which are fixed in size and contain data of the same type. So, for example, a list would be something which you can add to over time, whereas an array is something which has been done previously and you can't add any more to it. The main importance of an array is everything in there has something to do with everything else, so there is no anomaly. So 1D array. A 1D array is a single set of data which can be shown in a single row. A 2D array can be visualized in rows and columns, so for example this. So here the big array is this, but it is split into smaller arrays. So this is the first array, second and third. So the main premise is, if you were to look up something from these arrays, you could use something such as this. Let's just change that to 2 and then 3. So this is array 0, this is array 1, this is array 2. So array 2 would be this one. Then from in there, position 3 would be 0, 1, 2, 3. So it'd be L. Because it looks at the position within the array, the array number, then it looks at the position within the array. So 3D arrays. So 3D arrays are collections of 2D arrays, which you can visualize each 2D array being stored behind one another. So for example, this is one 2D array, this is another 2D array, this is another one, another one, another one, another one, and another one. So this is the first 2D array, this is the second one, and this is the third one. They're all stored behind one another. So to be able to use this, you would use the idea of the first array being a 0, second being a 1, third being a 2. So in this case, 2 would be the second array, 2 would be the third array of the 3D array of the second array, and the 2 would be the second position here, because obviously it starts counting from 0. So what type of array is this? This is a 2D array because it has multiple arrays inside one array. Items in 3D arrays are referred to by their 2D array number, followed by the something number and the something number. So the array number, where this one is position or index, but to be honest I don't know the terminology. Let's know how it works. Followed by their something number, a row and column. Sure, that's right, so a column apparently. C-O-L-U-M-N, column number. Perfect. So, linked lists. These are used data structures which benefit the flexibility and ease of use. They can be used to implement other data structures like stacks and queues. So linked lists. Linked lists consist of nodes. So nodes are like, say, something out of a main something. That's the best way of explaining it. Each node contains a data item and a pointer to the next node in a sequence. The use of pointers means that unlike arrays, data in linked lists don't have to be stored contiguously in memory, so they could also be defined as dynamic. So here's a graphical representation of a linked list containing the names of 3 animals in alphabetical order: elephant, rhino, zebra, nothing else. So adding nodes. To add tiger in the list alphabetically, the pointer of node 1 is updated to the point of the new node, which in turn points to the next in the sequence. So here, this is 0 to 1, 1 to 2, then 3 to 2, then 2 to nothing. So it just adds a new one in. And deleting nodes. To delete rhino, the point of node is updated to point to node 3. So node 1 would just be deleted. So describe the process of deleting football from the linked list. basketball 1, 1 football 2, 2 netball 3. Update the pointer of node 0 to point node 1, 2, 3. Oh, okay, yeah, but it goes from basketball to there. So 0 basketball 1 equals 2 netball 3. So delete data node 2, 1. Because that's data node 0. Okay, so because this is the node, then this is where it's going. This is a node, this is where it's going. This is the node, this is where it's going. So the node becomes the first of a separated list of something nodes ready to fill again. So empty nodes, perfect. So what kind of pointer is used to the last item in a linked list? So what type of pointer is used to be able to link the last two? Surely it's just a pointer. Yeah, that's about it. It's a pointer. A null pointer. Yeah. So queues. Queues are data structures where data items are always added to the end and removed from the front. These are often referred to as first in, first out data structures. Queues. Queues can be implemented using other data structures like arrays or linked lists. In either cases, 2 extra variables are required to identify the front and rear of the queue. Queues can be static, so that means they are fixed, or dynamic, that means they can change. So queue operations. Several operations are called out in queues. Enqueue adds and removes. Dequeue removes the displays. Is empty, checks if the queue has nothing in it. Is full, checks if like a not dynamic but a static queue is full or not, because dynamic queues can't be full, but you can just add as many as you want. So the use of queues. They have a lot of uses. For example, storing print jobs, so in order of what everything should be printed in. CPU scheduling, and breadth first transversal of a graph. So the only one that we actually understand there is printing. Linear circular. They can be both linear or circular. When an item of data is removed from the front of the linear queue, all the other items move one place. When adding an item of data is removed from the front of a circular queue, the only processing required is to update the 2 pointers identifying the new front and rear of the queues. How many extra variables would an array need to be implemented as a queue? It's a good question. How many extra variables? Queues can be implemented using such as other 2 extra variables need to be implemented. Queues. Queues have a wide range of uses in computer science, including print jobs, CPU scheduling, and the last one, which is breadth first survival of a graph or whatever. So which of the following would be used to refer to the element j? So 2D array, so j is in this one, so there's 1, 0, 1, 2. So that's a second array, the first position. So array 2, position 1. Genius. To describe the processes of adding a node with handball alphabetically, so 0, football, netball. So update the pointer of node something to point a new node. So handball is between football and netball, so node 1, but football is obviously node 1. 0 basketball, 1 football, 4. And then select the pointer of the new node to move to the final node. So football 4, handball 2. But there's a 4th thing that's been added. So when an item of data is removed from the front of a circular queue, the only processing required is to update the 10 pointers identifying the new front and rear. I don't think it's 10 pointers, 2 pointers. So describe how linear queues work. When an item of data is something from the front of a something queue, all the other items go back one place. Linear. When item of data is used, removed. This is the only suitable in a linear. So it's linear in a something queue. Otherwise, data processing can be long, slow, the hell is this? So linear queues. Queues are here. Implemented such as arrays, 2 extra variables, can be static or dynamic, remove blah blah blah, that, and can be linear or circular when an item is moved. All the items, they're also only suitable in small queues, otherwise data processing time can be, I said long, suitable in small queues, otherwise they can be long and excessive. Data processing time can be excessive or long, which is what I meant, just I didn't read it properly. So graphs, hash tables and stacks. I feel like I have heard of this but never heard of it at the same time, so we'll see. So graphs are data structures used to represent data items which have connections between them, such as locations on a map or products on a e-commerce website. So, why does this keep moving? Stop moving, you idiot. Graphs. Graphs consist of nodes or vertices which are connected by arcs or edges that can either be direct or indirect. Surely that should be indirect, but okay. A direct graph is one where the connections between nodes only go in one direction, so A to E, whereas in indirect they can go in any direction because connections are two ways. So graph traversal. There are two methods of traversing in a graph. Depth first, breadth first. Depth first traversal. That involves travelling down one route as far as possible before reversing and travelling as far down the next route as possible. In the graph shown, depth first traversal would involve visiting the nodes in the following order: A, B, E, D, A, B, E, C, D, G, F. I don't know where the G's come from, but okay. Breadth first. Breadth first traversal includes visiting all the adjoining nodes of each node in turn. In the graph shown, breadth traversal, first traversal, would involve visiting the nodes in order of A, B, C, E, D, F, G, so in order of where they're connected. What type of graph has connections between nodes that can only go in one direction? That is a direct graph. Direct. It's direct graph. Directed graph. Directed graph. Connections only go one direction. Directed graph is a directed graph. Directed graph, which is what you said. Length first traversal involves travelling down one route as possible. I don't think it's length though. Yeah, depth. Yep, because it is travelling one as fast as possible and then others. So, hash tables. A hash table is a data structure used for very large collections of data or where quick access to the data is required, such as customer records or password verification. Hash algorithms. Hashing algorithms allowed for efficient location and retrieval of data. The hashing algorithm generates indexes based on the key fields of set data. A common example of a hash algorithm is one which takes a key and divides it by the number of storage spaces available, then the remainder is used as the address. For example, the key is 389 here. If the keys 389, 221 and 560 need storing in hash table with 6 storage spaces, the process would go as following. Calculate the remainder when 738 is divided by 6. So that's 0. That means the first key should be stored in location 0. The second key has a remainder of 5, so it's stored in location 5. And the third key has a location remainder of 2, so it's stored in location 2. Collisions. A perfect hash algorithm will always generate a unique index. Should this not be the case, a collision is said to occur. When a collision occurs, a rehashing algorithm is used to determine the next available slot in which to store the data. Alternatively, we can create a separate data structure such as a linked list from each storage location and start collisions there. For example, using 362 would cause 2, so that means there would be a collision, however it's already filled. So the next available location is 3, so it would be stored there. What term is used when a hashing algorithm does not produce a unique key? Collision. Perfection. Use the remainder algorithm to sort the following keys into the hash table. So 300 mod 6 would give a remainder of 0, so it would be in location 0. That divided by 6 would be, definitely not reaching for a calculator, divided by 6, that would be, oh no, 59 times 6, so that would be a remainder of 359 minus answer is 5, so it would be 5, so it would be stored in location 5. 222 mod 6 would be 222 divided by 6, 37, so it's 0. So it would be stored in location 1, but that's the next available one. 718 divided by 6 would give a remainder of 718 divided by 6, so that is 1119 times 6, so that is a remainder of 4. So it would be stored in location 4, but that's not filled yet. Perfect. Stacks. A stack is a data structure where data items are always added and removed from the top. It's often referred to as last in, first out. So, a stack of data structure where data items are always added and removed from the top is often referred to as last in, first out data structure. Stacks can be implemented using other data structures like arrays or linked lists. In other cases, an extra variable is required to identify the top of the stack. Stack operations: push would add something on top of the stack, pop would remove, peek would display the items at the top without removing it, empty would check if it's empty, full would check if it's full. Uses: the most common uses of stacks is to reverse the order of a set of data items as they are popped in the opposite order to where they are pushed in the stack. They are also used by processors to handle interruptions. Stacks can be static, that means fixed in size, or dynamic, that means they're able to get bigger. Errors: stack overflow errors can occur in static stacks when attempting to push an item onto a stack that is full. Similarly, when trying to pop from an empty stack, a stack underflow error could occur. So what kind of error occurs when static stacks when attempting to push them on a stack that is full? A stack overflow. Perfection. What's next? In which order with breadth first? So that'd be A, B, C, A, B, C, E, D, F, G. Perfect. It just goes that way. So hashing algorithms allow for effective storage. So not storage of data. What else are you doing with the data? You're sorting and storing it there. It allows for collection of data, blah blah blah. And what does it allow for? It allows for effective location and retrieval. Location is okay. And retrieval of data. Okay, I see how it is. So pop, that gets it. Push, adds it. Is full, checks if it's full. Is empty, checks if it's empty. And something displays the top. So what displays the top of the stack? I do know this definitely. And do not need to check while I'm checking peek. Considering we don't actually need to know those parts, that is pretty impressive. Stacks can be implemented using other data structures such as array and linked lists. In either case, an extra list is required to identify the top of the stack. An extra list? Don't think it's an extra list. An extra variable structure memory, an extra structure variable. Oh no. Well, we were close. We almost went 100% on that one. And next one is trees. trees. Unlike other data structures in computer science, trees represent data hierarchy. So roots, branches, sub-branches. So roots obviously is the thing that grows a tree. Trees have branches, branches have sub-branches. So tree construction. The rules for creating trees are each node must only be connected with one parent node and one more child. There so must never be a connection directly between nodes on the same level of the hierarchy. So, tree traversal. There are 3 ways to navigate tree traversal, which is pre-order, in-order, and post-order. Pre-order is it starts with a root node and visits each of the nodes from left to right. So, tiger, zebra, rhino, lion, gazelle, giraffe, hippo, elephant. In-order traversal starts with the nodes on the left subtree, then visits the roots in order followed by the nodes on the right subtree. So, lion, zebra, gazelle, giraffe, tiger, elephant, rhino, hippo. Wait, what? Hippo, rhino? But rhino is less left. Okay, and post-order. Post-order starts by visiting the nodes in the left subtree from bottom to top, and the right subtree bottom to top before finishing with the root node. So I'd finish with tiger. So it goes lion, gazelle, giraffe, zebra, elephant, hippo, rhino, then tiger. So what order would pre-order traversal go? So it's got purple, blue, red. Pre-order traversal? What's it? Oh, that's post-order traversal. In order and post order would just go down. So it'd be orange, red, green. Orange, red, green, would it not? Post order starts with root node, with all the roots. So tiger. Oh, so orange, red, purple, blue, green, yellow. So this one. Yeah. Unlike the other data structures in a computer, trees represent data with a hierarchy. So binary search in trees. Oh dear. A binary search in a tree is a data structure used for efficient searching of data. Binary search trees share the same properties as trees, with the exception that each node can have no more than 2 child nodes. Binary search trees are very quick to search. Storing data. After storing the first piece of data in the root node, the second entry is stored in a child node to the left of the root of its has a lesser value. The second entry is stored on a child node to the right if it has a greater value. So if this has a bigger value than this, it would be stored on the right. So the procedure for storing tiger, zebra, lion, gazelle, and rhino in the order gives us the following. Tiger is a root node, then zebra is greater than tiger alphabetically, so it's stored as a child node to the right. Step 2. Lion comes before zebra, and so it's stored as a child node to the left. And then the same is done with gazelle and rhino, where gazelle comes later. So binary search trees, parent node, child node, and then the bigger one, and this is alphabetically. So complete the binary search for the following results. The root node is 12, as we see there. So 13 is greater than 12, so it goes on to the right. Perfect. 9 is less, so it goes on to the left. 25 is greater than 12 and greater than 13, so it goes on a branch road of 13 and goes on the right. And 4 is less than 12 and less than 9, so it goes on a branch row of 4 and is to the left. Ways to order. Pre-order, in-order, it's not out-order, pre-order, in-order, post-order. That seems familiar, post-order, yep. So, complete the binary search. The root node is lime. Cherry is less than lime alphabetically, so it goes on the left. Kiwi is less than lime, but greater than cherry, so it goes on the branch node of cherry, but to the right. Well, that diagram is inaccurate then. An apple is less than lime and cherry alphabetically. That means it goes on the branch node of cherry to the left because it's less than. Pear is greater than lime, so it goes on the right. It's the only one that goes on the right. Lonely. The second entry to a binary search tree is stored in a child node to the left if it has a lesser value. And that is data structures done.